A Stirling engine is a heat engine operating by cyclic compression and expansion of air or other gas, the working fluid, at different temperature levels such that there is a net conversion of heat energy to mechanical work. Or more specifically, a closed-cycle regenerative heat engine with a permanently gaseous working fluid, where closed cycle is defined as a thermodynamic system in which the working fluid is permanently contained within the system, and regenerative describes the use of a specific type of internal heat exchanger and thermal store, known as the regenerator. It is the inclusion of a regenerator that differentiates the Stirling engine from other closed-cycle hot air engines. Originally conceived in 1816 as an industrial prime mover to rival the steam engine, its practical use was largely confined to low-power domestic applications for over a century. The Stirling engine is noted for its high efficiency compared to steam engines, quiet operation, and the ease with which it can use almost any heat source. This compatibility with alternative and renewable energy sources has become increasingly significant as the price of conventional fuels rises, and also in light of concerns such as peak oil and climate change. This engine is currently exciting interest as the core component of micro-combined heat and power units, in which it is more efficient and safer than a comparable steam engine. Name and classification: Robert Stirling was a Scottish minister who invented the first practical example of a closed-cycle air engine in 1816, and it was suggested by Fleming Jenkin as early as 1884 that all such engines should therefore generically be called Stirling engines. This naming proposal found little favour, and the various types on the market continue to be known by the name of their individual designers or manufacturers, for example Ryder's, Robinson's, or Heinrichs air engine. In the 1940s, the Phillips Company was seeking a suitable name for its own version of the air engine, which by that time had been tested with working fluids other than air, and decided upon Stirling engine in April 1945. However, nearly 30 years later, Graham Walker still had cause to bemoan the fact such terms as hot air engine continued to be used interchangeably with Stirling engine, which itself was applied widely and indiscriminately. A situation which continues to this day. Like the steam engine, the Stirling engine is traditionally classified as an external combustion engine, as all heat transfers to and from the working fluid take place through a solid boundary, thus isolating the combustion process and any contaminants it may produce from the working parts of the engine. This contrasts with an internal combustion engine where heat input is by combustion of a fuel within the body of the working fluid. There are many possible implementations of the Stirling engine, most of which fall into the category of reciprocating piston engine. History, invention and early development. The Stirling engine was invented and patented by Robert Stirling in 1816. It followed earlier attempts at making an air engine but was probably the first to be put to practical use when in 1818 an engine built by Stirling was employed pumping water in a quarry. The main subject of Stirling's original patent was a heat exchanger which he called an economizer for its enhancement of fuel economy in a variety of applications. The patent also described in detail the employment of one form of the economizer in his unique closed-cycle air engine design, in which application it is now generally known as a regenerator. Subsequent development by Robert Stirling and his brother James, an engineer, resulted in patents for various improved configurations of the original engine, including pressurization, which had by 1843 sufficiently increased power output to drive all the machinery at a Dundee iron foundry. Though it has been disputed, it is widely supposed that as well as saving fuel, the inventors were motivated to create a safer alternative to the steam engines of the time, whose boilers frequently exploded, causing many injuries and fatalities. The need for Stirling engines to run at very high temperatures to maximize power and efficiency exposed limitations in the materials of the day, and the few engines that were built in those early years suffered unacceptably frequent failures. For example, the Dundee foundry engine was replaced by a steam engine after 3 hot cylinder failures in 4 years. Later 19th century. Subsequent to the failure of the Dundee foundry engine, there is no record of the Stirling brothers having any further involvement with air engine development, and a Stirling engine never again competed with steam as an industrial-scale power source. However, from about 1860 smaller engines of the Stirling hot air type were produced in substantial numbers, finding applications wherever a reliable source of low to medium power was required, such as raising water or providing air for church organs. These generally operated at lower temperatures so as not to tax available materials, so were relatively inefficient. Their selling point was that, unlike a steam engine, they could be operated safely by anybody capable of managing a fire. Several types remained in production beyond the end of the century, but apart from a few minor mechanical improvements, the design of the Stirling engine in general stagnated during this period. 20th century revival. During the early part of the 20th century, the role of the Stirling engine as a domestic motor was gradually taken over by the electric motor and small internal combustion engines. By the late 1930s, it was largely forgotten, only produced for toys and a few small ventilating fans. Around that time, Philips was seeking to expand sales of its radios into parts of the world where mains electricity was unavailable and batteries were not consistently available. Philips management decided that offering a low-power portable generator would facilitate such sales and asked a group of engineers at the company's research lab in Eindhoven to evaluate alternative ways of achieving this aim. After a systematic comparison of various prime movers, the team decided to go forward with the Stirling engine, citing its quiet operation and ability to run on a variety of heat sources. They were also aware that, unlike steam and internal combustion engines, virtually no serious development work had been carried out on the Stirling engine for many years and asserted that modern materials and know-how should enable great improvements. By 1951, the 180-200 W generator set designated Northern Mariana Islands, 1002 ca was ready for production and an initial batch of 250 was planned, but soon it became clear that they could not be made at a competitive price. Additionally, the advent of transistor radios and their much lower power requirements meant that the original rationale for the set was disappearing. Approximately 150 of these sets were eventually produced. Some found their way into university and college engineering departments around the world, giving generations of students a valuable introduction to the Stirling engine. In parallel with the bungalow set, Philips developed experimental Stirling engines for a wide variety of applications and continued to work in the field until the late 1970s, but only achieved commercial success with the reverse Stirling engine curricula. However, they filed a large number of patents and amassed a wealth of information, which they licensed to other companies and which formed the basis of much of the development work in the modern era. Functional description: the engine is designed so that the working gas is generally compressed in the colder portion of the engine and expanded in the hotter portion, resulting in a net conversion of heat into work. An internal regenerative heat exchanger increases the Stirling engine's thermal efficiency compared to simpler hot air engines lacking this feature. Key components: as a consequence of closed-cycle operation, the heat driving a Stirling engine must be transmitted from a heat source to the working fluid by heat exchangers and finally to a heat sink. A Stirling engine system has at least one heat source, one heat sink and up to 5 heat exchangers. Some types may combine or dispense with some of these. Heat source: the heat source may be provided by the combustion of a fuel and, since the combustion products do not mix with the working fluid and hence do not come into contact with the internal parts of the engine, a Stirling engine can run on fuels that would damage other types of engines' internals, such as landfill gas which contains silicon. Other suitable heat sources include concentrated solar energy, geothermal energy, nuclear energy, waste heat and bioenergy. If solar power is used as a heat source, regular solar mirrors and solar dishes may be utilized. The use of Fresnel lenses and mirrors has also been advocated, for example in planetary surface exploration. Solar-powered Stirling engines are increasingly popular as they offer an environmentally sound option for producing power, while some designs are economically attractive in development projects. Heater/hot side heat exchanger: in small, low-power engines this may simply consist of the walls of the hot space, but where larger powers are required a greater surface area is needed in order to transfer sufficient heat. Typical implementations are internal and external fins or multiple small bore tubes. Designing Stirling engine heat exchangers is a balance between high heat transfer with low viscous pumping losses and low dead space. With engines operating at high powers and pressures, the heat exchangers on the hot side must be made of alloys that retain considerable strength at temperature and that will also not corrode or creep. Regenerator. In a Stirling engine, the regenerator is an internal heat exchanger and temporary heat store placed between the hot and cold spaces such that the working fluid passes through it first in one direction then the other, taking heat from the fluid in one direction, and returning it in the other. It can be as simple as metal mesh or foam, and benefits from high surface area, high heat capacity, low conductivity and low flow friction. Its function is to retain within the system that heat which would otherwise be exchanged with the environment at temperatures intermediate to the maximum and minimum cycle temperatures, thus enabling the thermal efficiency of the cycle to approach the limiting Carnot efficiency. The primary effect of regeneration in a Stirling engine is to increase the thermal efficiency by recycling internal heat which would otherwise pass through the engine irreversibly. As a secondary effect, increased thermal efficiency yields a higher power output from a given set of hot and cold end heat exchangers. It is these which usually limit the engine's heat throughput. In practice this additional power may not be fully realized as the additional dead space and pumping loss inherent in practical regenerators reduces the potential efficiency gains from regeneration. The design challenge for a Stirling engine regenerator is to provide sufficient heat transfer capacity without introducing too much additional internal volume or flow resistance. These inherent design conflicts are one of many factors which limit the efficiency of practical Stirling engines. A typical design is a stack of fine metal wire meshes, with low porosity to reduce dead space, and with the wire axis perpendicular to the gas flow to reduce conduction in that direction and to maximize convective heat transfer. The regenerator is the key component invented by Robert Stirling and its presence distinguishes a true Stirling engine from any other closed-cycle hot air engine. Many small toy Stirling engines, particularly low-temperature difference types, do not have a distinct regenerator component and might be considered hot air engines. However, a small amount of regeneration is provided by the surface of the displacer itself and the nearby cylinder wall, or similarly the passage connecting the hot and cold cylinders of an alpha configuration engine. Cooler/cold side heat exchanger. In small, low-power engines this may simply consist of the walls of the cold space, but where larger powers are required a cooler using a liquid like water is needed in order to transfer sufficient heat. Heat sink. The heat sink is typically the environment at ambient temperature. In the case of medium to high power engines, a radiator is required to transfer the heat from the engine to the ambient air. Marine engines can use the ambient water. In the case of combined heat and power systems, the engine's cooling water is used directly or indirectly for heating purposes. Alternatively, heat may be supplied at ambient temperature and a heat sink maintained at a lower temperature by such means as cryogenic fluid or iced water. Displacer. The displacer is a special-purpose piston, used in beta and gamma-type Stirling engines, to move the working gas back and forth between the hot and cold heat exchangers. Depending on the type of engine design, the displacer may or may not be sealed to the cylinder, that is it may be a loose fit within the cylinder, allowing the working gas to pass around it as it moves to occupy the part of the cylinder beyond. Configurations. There are three major types of Stirling engines, that are distinguished by the way they move the air between the hot and cold areas. The alpha configuration has two power pistons, one in a hot cylinder, one in a cold cylinder, and the gas is driven between the two by the pistons. It is typically in a V formation with the pistons joined at the same point on a crankshaft. The beta configuration has a single cylinder with a hot end and a cold end, containing a power piston and a displacer which drives the gas between the hot and cold ends. It is typically used with a rhombic drive to achieve the phase difference between the displacer and power pistons, but they can be joined 90 degrees out of phase on a crankshaft. The gamma configuration has two cylinders, one containing a displacer, with a hot and a cold end, and one for the power piston. They are joined to form a single space with the same pressure in both cylinders. The pistons are typically in parallel and joined 90 degrees out of phase on a crankshaft. Alpha configuration operation. An alpha Stirling contains two power pistons and separate cylinders, one hot and one cold. The hot cylinder is situated inside the high-temperature heat exchanger and the cold cylinder is situated inside the low-temperature heat exchanger. This type of engine has a high power-to-volume ratio but has technical problems due to the usually high temperature of the hot piston and the durability of his seals. In practice, this piston usually carries a large insulating head to move the seals away from the hot zone at the expense of some additional dead space. The following diagrams do not show internal heat exchangers in the compression and expansion spaces, which are needed to produce power. A regenerator would be placed in the pipe connecting the two cylinders. Beta configuration operation. A beta Stirling has a single power piston arranged within the same cylinder on the same shaft as a displacer piston. The displacer piston is a loose fit and does not extract any power from the expanding gas but only serves to shuttle the working gas between the hot and cold heat exchangers. When the working gas is pushed to the hot end of the cylinder it expands and pushes the power piston. When it is pushed to the cold end of the cylinder it contracts and the momentum of the machine, usually enhanced by a flywheel, pushes the power piston the other way to compress the gas. Unlike the alpha type, the beta type avoids the technical problems of hot-moving seals. Again, the following diagrams do not show any internal heat exchangers or a regenerator, which would be placed in the gas path around the displacer. If a regenerator is used in a beta engine, it is usually in the position of the displacer and moving, often as a volume of wire mesh. Gamma configuration operation. A gamma Stirling is simply a beta Stirling in which the power piston is mounted in a separate cylinder alongside the displacer piston cylinder, but is still connected to the same flywheel. The gas in the two cylinders can flow freely between them and remains a single body. This configuration produces a lower compression ratio because of the volume of the connection between the two but is mechanically simpler and often used in multi-cylinder Stirling engines. Other types. Other Stirling configurations continue to interest engineers and inventors. The rotary Stirling engine seeks to convert power from the Stirling cycle directly into torque, similar to the rotary combustion engine. No practical engine has yet been built but a number of concepts, models and patents have been produced, for example the quasi-turbine engine. The hybrid between piston and rotary configuration is a double-acting engine. This design rotates the displacers on either side of the power piston. Another alternative is the fluidine engine, which uses hydraulic pistons to implement the Stirling cycle. The work produced by a fluidine engine goes into pumping the liquid. In its simplest form, the engine contains a working gas, a liquid and two non-return valves. The Ringbom engine concept published in 1907 has no rotary mechanism or linkage for the displacer. This is instead driven by a small auxiliary piston, usually a thick displacer rod, with the movement limited by stops. The two-cylinder Stirling with Ross yoke is a two-cylinder Stirling engine connected with a special yoke. The engine configuration yoke setup was invented by Andy Ross. The Franchot engine is a double-acting engine invented by a Euro-Franchotti Euro-1 registered trademark in the 19th century. A double-acting engine is one where both sides of the piston are acted upon by the pressure of the working fluid. One of the simplest forms of a double-acting machine, the Franchot engine consists of two pistons and two cylinders and acts like two separate alpha machines. In the Franchot engine, each piston acts in two gas phases, which makes more efficient use of the mechanical components than a single-acting alpha machine. However, a disadvantage of this machine is that one connecting rod must have a sliding seal at the hot side of the engine, which is a difficult task when dealing with high pressures and high temperatures. Free-piston Stirling engines. Free-piston Stirling engines include those with liquid pistons and those with diaphragms as pistons. In a free-piston device, energy may be added or removed by an electrical linear alternator, pump or other coaxial device. This avoids the need for a linkage, and reduces the number of moving parts. In some designs, friction and wear are nearly eliminated by the use of non-contact gas bearings or very precise suspension through planar springs. 4 basic steps in the cycle of AA Euro OE free piston a Euro Stirling engine. The power piston is pushed outwards by the expanding gas, thus doing work. Gravity plays no role in the cycle. The gas volume in the engine increases and therefore the pressure reduces, which will cause a pressure difference across the displacer rod to force the displacer towards the hot end. When the displacer moves, the piston is almost stationary and therefore the gas volume is almost constant. This step results in the constant volume cooling process, which reduces the pressure of the gas. The reduced pressure now arrests the outward motion of the piston and it begins to accelerate towards the hot end again, and by its own inertia, compresses the now cold gas, which is mainly in the cold space. As the pressure increases, a point is reached where the pressure differential across the displacer rod becomes large enough to begin to push the displacer rod towards the piston and thereby collapsing the cold space and transferring the cold, compressed gas towards the hot side in an almost constant volume process. As the gas arrives in the hot side, the pressure increases and begins to move the piston outwards to initiate the expansion step as explained in. In the early 1960s, W.T. Beale invented a free piston version of the Stirling engine in order to overcome the difficulty of lubricating the crank mechanism. While the invention of the basic free piston Stirling engine is generally attributed to Beale, independent inventions of similar types of engines were made by E. H. Cook Yarborough and C. West at the Harwell laboratories of the UK. G. M. Benson also made important early contributions and patented many novel free piston configurations. What appears to be the first mention of a Stirling cycle machine using freely moving components is a British patent disclosure in 1876. This machine was envisaged as a refrigerator. The first consumer product to utilize a free piston Stirling device was a portable refrigerator manufactured by Twine-Bird Corporation of Japan and offered in the U.S. by Coleman in 2004. Flat Stirling engine. Design of the flat double-acting Stirling engine solves the drive of a displacer with the help of the fact that areas of the hot and cold pistons of the displacer are different. The drive does so without any mechanical transmission. Using diaphragms eliminates friction and need for lubricants. When the displacer is in motion, the generator holds the working piston in the limit position, which brings the engine working cycle close to an ideal Stirling cycle. The ratio of the area of the heat exchangers to the volume of the machine increases by the implementation of a flat design. Flat design of the working cylinder approximates thermal process of the expansion and compression closer to the isothermal one. The disadvantage is a large area of the thermal insulation between the hot and cold space. Thermoacoustic cycle. Thermoacoustic devices are very different from Stirling devices, although the individual path traveled by each working gas molecule does follow a real Stirling cycle. These devices include the thermoacoustic engine and thermoacoustic refrigerator. High-amplitude acoustic standing waves cause compression and expansion analogous to a Stirling power piston, while out-of-phase acoustic traveling waves cause displacement along a temperature gradient, analogous to a Stirling displacer piston. Thus a thermoacoustic device typically does not have a displacer, as found in a beta or gamma Stirling. Other developments. Starting in 1986, Infinia Corporation began developing both highly reliable pulsed free piston Stirling engines, and thermoacoustic coolers using related technology. The published design uses flexural bearings and hermetically sealed helium gas cycles, to achieve tested reliabilities exceeding 20 years. As of 2010, the corporation had amassed more than 30 patents, and developed a number of commercial products for both combined heat and power, and solar power. More recently, NASA has considered nuclear decay-heated Stirling engines for extended missions to the outer solar system. At the recent Cable Tech Expo put on by the Society of Cable Telecommunications Engineers, Dean Carman took the stage with Time Warner Cable Chief Technology Officer Mike Larchbar to announce a new initiative between his company DCAR Research and the SCTE. Carman refers to it as a Stirling engine. Theory. The idealized Stirling cycle consists of 4 thermodynamic processes acting on the working fluid: isothermal expansion. The expansion space and associated heat exchanger are maintained at a constant high temperature, and the gas undergoes near isothermal expansion, absorbing heat from the hot source. Constant volume heat removal. The gas is passed through the regenerator, where it cools, transferring heat to the regenerator for use in the next cycle. Isothermal compression. The compression space and associated heat exchanger are maintained at a constant low temperature, so the gas undergoes near isothermal compression, rejecting heat to the cold sink, constant volume heat addition. The gas passes back through the regenerator where it recovers much of the heat transferred into, heating up on its way to the expansion space. Theoretical thermal efficiency equals that of the hypothetical Carnot cycle, that is the highest efficiency attainable by any heat engine. However, though it is useful for illustrating general principles, the ideal cycle deviates substantially from practical Stirling engines. It has been argued that its indiscriminate use in many standard books on engineering thermodynamics has done a disservice to the study of Stirling engines in general. Other real-world issues reduce the efficiency of actual engines, due to limits of convective heat transfer, and viscous flow. There are also practical mechanical considerations. For instance, a simple kinematic linkage may be favored over a more complex mechanism needed to replicate the idealized cycle, and limitations imposed by available materials such as non-ideal properties of the working gas, thermal conductivity, tensile strength, creep, rupture strength, and melting point. A question that often arises is whether the ideal cycle with isothermal expansion and compression is in fact the correct ideal cycle to apply to the Stirling engine. Professor C.J. Rallis has pointed out that it is very difficult to imagine any condition where the expansion and compression spaces may approach isothermal behavior, and it is far more realistic to imagine these spaces as adiabatic. An ideal analysis where the expansion and compression spaces are taken to be adiabatic with isothermal heat exchangers and perfect regeneration was analyzed by Rallis and presented as a better ideal yardstick for Stirling machinery. He called this cycle the Pseudo Stirling cycle or ideal adiabatic Stirling cycle. An important consequence of this ideal cycle is that it does not predict Carnot efficiency. A further conclusion of this ideal cycle is that maximum efficiencies are found at lower compression ratios, a characteristic observed in real machines. In an independent work, T. Finkelstein also assumed adiabatic expansion and compression spaces in his analysis of Stirling machinery operation. Since the Stirling engine is a closed cycle, it contains a fixed mass of gas called the working fluid, most commonly air, hydrogen or helium. In normal operation, the engine is sealed and no gas enters or leaves the engine. No valves are required, unlike other types of piston engines. The Stirling engine, like most heat engines, cycles through four main processes: cooling, compression, heating and expansion. This is accomplished by moving the gas back and forth between hot and cold heat exchangers, often with a regenerator between the heater and cooler. The hot heat exchanger is in thermal contact with an external heat source, such as a fuel burner, and the cold heat exchanger being in thermal contact with an external heat sink, such as air fins. A change in gas temperature will cause a corresponding change in gas pressure, while the motion of the piston causes the gas to be alternately expanded and compressed. The gas follows the behavior described by the gas laws, which describe how a gas pressure, temperature and volume are related. When the gas is heated, because it is in a sealed chamber, the pressure rises and this then acts on the power piston to produce a power stroke. When the gas is cooled, the pressure drops, and this means that less work needs to be done by the piston to compress the gas on the return stroke, thus yielding a net power output. The ideal Stirling cycle is unattainable in the real world, and the actual Stirling cycle is inherently less efficient than the Otto cycle of internal combustion engines. The efficiency of Stirling machines is linked to the environmental temperature. A higher efficiency is obtained when the weather is cooler, thus making this type of engine less interesting in places with warmer climates. As with other external combustion engines, Stirling engines can use heat sources other than from combustion of fuels. When one side of the piston is open to the atmosphere, the operation is slightly different. As the sealed volume of working gas comes in contact with the hot side, it expands, doing work on both the piston and on the atmosphere. When the working gas contacts the cold side, its pressure drops below atmospheric pressure and the atmosphere pushes on the piston and does work on the gas. To summarize, The Stirling engine uses the temperature difference between its hot end and cold end to establish a cycle of a fixed mass of gas, heated and expanded, and cooled and compressed, thus converting thermal energy into mechanical energy. The greater the temperature difference between the hot and cold sources, the greater the thermal efficiency. The maximum theoretical efficiency is equivalent to the Carnot cycle, however the efficiency of real engines is less than this value due to friction and other losses. Very low-power engines have been built which will run on a temperature difference of as little as 0.5 K. In a displacer-type Stirling engine you have one piston and one displacer. A temperature difference is required between the top and bottom of the large cylinder in order to run the engine. In the case of the low temperature difference Stirling engine, temperature difference between your hand and the surrounding air can be enough to run the engine. The power piston in the displacer-type Stirling engine is tightly sealed and is controlled to move up and down as the gas inside expands. The displacer on the other hand is very loosely fitted so that air can move freely between the hot and cold sections of the engine as the piston moves up and down. The displacer moves up and down to control the heating and cooling of the gas in the engine. There are two positions, when the displacer is near the top of the large cylinder. Inside the engine most of the gas has been heated by the heat source and it expands. This causes the pressure to increase which forces the piston up. When the displacer is near the bottom of the large cylinder, most of the gas in the engine has now cooled and contracts causing the pressure to decrease, which in turn allows the piston to move down and compress the gas. Pressurization. In most high-power Stirling engines, both the minimum pressure and mean pressure of the working fluid are above atmospheric pressure. This initial engine pressurization can be realized by a pump, or by filling the engine from a compressed gas tank, or even just by sealing the engine when the mean temperature is lower than the mean operating temperature. All of these methods increase the mass of working fluid in the thermodynamic cycle. All of the heat exchangers must be sized appropriately to supply the necessary heat transfer rates. If the heat exchangers are well designed and can supply the heat flux needed for convective heat transfer, then the engine will in a first approximation produce power in proportion to the mean pressure, as predicted by the West number, and Beale number. In practice, the maximum pressure is also limited to the safe pressure of the pressure vessel. Like most aspects of Stirling engine design, optimization is multivariate, and often has conflicting requirements. A difficulty of pressurization is that while it improves the power, the heat required increases proportionately to the increased power. This heat transfer is made increasingly difficult with pressurization since increased pressure also demands increased thicknesses of the walls of the engine which, in turn, increase the resistance to heat transfer. Lubricants and friction. At high temperatures and pressures, the oxygen in air pressurized crankcases, or in the working gas of hot air engines, can combine with the engine's lubricating oil and explode. At least one person has died in such an explosion. Lubricants can also clog heat exchangers, especially the Regenerator. For these reasons, designers prefer non-lubricated, low coefficient of friction materials, with low normal forces on the moving parts, especially for sliding seals. Some designs avoid sliding surfaces altogether by using diaphragms for sealed pistons. These are some of the factors that allow Stirling engines to have lower maintenance requirements and longer life than internal combustion engines. Analysis. Comparison with internal combustion engines. In contrast to internal combustion engines, Stirling engines have the potential to use renewable heat sources more easily, to be quieter, and to be more reliable with lower maintenance. They are preferred for applications that value these unique advantages, particularly if the cost per unit energy generated is more important than the capital cost per unit power. On this basis, Stirling engines are cost competitive up to about 100 a kilowatt. Compared to an internal combustion engine of the same power rating, Stirling engines currently have a higher capital cost and are usually larger and heavier. However, they are more efficient than most internal combustion engines. Their lower maintenance requirements make the overall energy cost comparable. The thermal efficiency is also comparable, ranging from 15% to 30%. For applications such as micro-CHP, A Stirling engine is often preferable to an internal combustion engine. Other applications include water pumping, astronautics, and electrical generation from plentiful energy sources that are incompatible with the internal combustion engine, such as solar energy, and biomass such as agricultural waste and other waste such as domestic refuse. Stirlings are also used as a marine engine in Swedish Gotland-class submarines. However, Stirling engines are generally not price competitive as an automobile engine, due to high cost per unit power, low power density and high material costs. Basic analysis is based on the closed-form Schmidt analysis. Advantages: Stirling engines can run directly on any available heat source, not just one produced by combustion, so they can run on heat from solar, geothermal, biological, nuclear sources or waste heat from industrial processes. A continuous combustion process can be used to supply heat, so those emissions associated with the intermittent combustion processes of a reciprocating internal combustion engine can be reduced. Some types of Stirling engines have the bearings and seals on the cool side of the engine, where they require less lubricant and last longer than equivalents on other reciprocating engine types. The engine mechanisms are in some ways simpler than other reciprocating engine types. No valves are needed, and the burner system can be relatively simple. Crude Stirling engines can be made using common household materials. A Stirling engine uses a single-phase working fluid which maintains an internal pressure close to the design pressure, and thus for a properly designed system the risk of explosion is low. In comparison, a steam engine uses a two-phase gas-liquid working fluid, so a faulty overpressure relief valve can cause an explosion. In some cases, low operating pressure allows the use of lightweight cylinders. They can be built to run quietly and without an air supply, for air-independent propulsion use in submarines. They start easily and run more efficiently in cold weather, in contrast to the internal combustion which starts quickly in warm weather, but not in cold weather. A Stirling engine used for pumping water can be configured so that the water cools the compression space. This is most effective when pumping cold water. They are extremely flexible. They can be used as CHP in the winter and as coolers in summer. Waste heat is easily harvested, making Stirling engines useful for dual-output heat and power systems. Disadvantages: size and cost issues. Stirling engine designs require heat exchangers for heat input and for heat output, and these must contain the pressure of the working fluid, where the pressure is proportional to the engine power output. In addition, the expansion side heat exchanger is often at very high temperature, so the materials must resist the corrosive effects of the heat source, and have low creep. Typically these material requirements substantially increase the cost of the engine. The materials and assembly costs for a high-temperature heat exchanger typically accounts for 40% of the total engine cost. All thermodynamic cycles require large temperature differentials for efficient operation. In an external combustion engine, the heater temperature always equals or exceeds the expansion temperature. This means that the metallurgical requirements for the heater material are very demanding. This is similar to a gas turbine, but is in contrast to an Otto engine or diesel engine, where the expansion temperature can far exceed the metallurgical limit of the engine materials, because the input heat source is not conducted through the engine, so engine materials operate closer to the average temperature of the working gas. The Stirling cycle is not actually achievable. The real cycle in Stirling machines is less efficient than the theoretical Stirling cycle. Also, the efficiency of the Stirling cycle is lower where the ambient temperatures are mild, while it would give its best results in a cool environment, such as northern countries' winters. Dissipation of waste heat is especially complicated because the coolant temperature is kept as low as possible to maximize thermal efficiency. This increases the size of the radiators, which can make packaging difficult. Along with materials cost, this has been one of the factors limiting the adoption of Stirling engines as automotive prime movers. For other applications such as ship propulsion and stationary microgeneration systems using combined heat and power, high power density is not required. Power and torque issues. Stirling engines, especially those that run on small temperature differentials, are quite large for the amount of power that they produce. This is primarily due to the heat transfer coefficient of gaseous convection, which limits the heat flux that can be attained in a typical cold heat exchanger to about 500 AW/m2 a K, and in a hot heat exchanger to about 500 euro 5000 AW/m2 a K. Compared with internal combustion engines, this makes it more challenging for the engine designer to transfer heat into and out of the working gas. Because of the thermal efficiency, the required heat transfer grows with lower temperature difference, and the heat exchanger surface for 1 kilowatt output grows with second power of 1/delta-T. Therefore the specific cost of very low temperature difference engines is very high. Increasing the temperature differential and/or pressure allows Stirling engines to produce more power, assuming the heat exchangers are designed for the increased heat load, and can deliver the convected heat flux necessary. A Stirling engine cannot start instantly. It literally needs to warm up. This is true of all external combustion engines, but the warm-up time may be longer for Stirlings than for others of this type, such as steam engines. Stirling engines are best used as constant-speed engines. Power output of a Stirling tends to be constant, and to adjust it can sometimes require careful design and additional mechanisms. Typically, changes in output are achieved by varying the displacement of the engine, or by changing the quantity of working fluid, or by altering the piston displacer phase angle, or in some cases simply by altering the engine load. This property is less of a drawback in hybrid electric propulsion or base load utility generation, where constant power output is actually desirable. Gas choice issues. The gas used should have a low heat capacity, so that a given amount of transferred heat leads to a large increase in pressure. Considering this issue, helium would be the best gas because of its very low heat capacity. Air is a viable working fluid, but the oxygen in a highly pressurized air engine can cause fatal accidents caused by lubricating oil explosions. Following one such accident, Phillips pioneered the use of other gases to avoid such risk of explosions. Hydrogen's low viscosity and high thermal conductivity make it the most powerful working gas, primarily because the engine can run faster than with other gases. However, due to hydrogen absorption, and given the high diffusion rate associated with this low molecular weight gas, particularly at high temperatures, H2 will leak through the solid metal of the heater. Diffusion through carbon steel is too high to be practical, but may be acceptably low for metals such as aluminum, or even stainless steel. Certain ceramics also greatly reduce diffusion. Hermetic pressure vessel seals are necessary to maintain pressure inside the engine without replacement of lost gas. For high-temperature differential engines, auxiliary systems may need to be added to maintain high-pressure working fluid. These systems can be a gas storage bottle or a gas generator. Hydrogen can be generated by electrolysis of water, the action of steam on red-hot carbon-based fuel, by gasification of hydrocarbon fuel, or by the reaction of acid on metal. Hydrogen can also cause the embrittlement of metals. Hydrogen is a flammable gas, which is a safety concern if released from the engine. Most technically advanced Stirling engines, like those developed for United States government labs, use helium as the working gas, because it functions close to the efficiency and power density of hydrogen with fewer of the material containment issues. Helium is inert, and hence not flammable. Helium is relatively expensive, and must be supplied as bottled gas. One test showed hydrogen to be 5% more efficient than helium in the GPU-3 Stirling engine. The researcher Alan Organ demonstrated that a well-designed air engine is theoretically just as efficient as a helium or hydrogen engine, but helium and hydrogen engines are several times more powerful per unit volume. Some engines use air or nitrogen as the working fluid. These gases have much lower power density, but they are more convenient to use and they minimize the problems of gas containment and supply. The use of compressed air in contact with flammable materials or substances such as lubricating oil introduces an explosion hazard, because compressed air contains a high partial pressure of oxygen. However, oxygen can be removed from air through an oxidation reaction, or bottled nitrogen can be used, which is nearly inert and very safe. Other possible lighter-than-air gases include methane, and ammonia. Applications. Applications of the Stirling engine range from heating and cooling to underwater power systems. A Stirling engine can function in reverse as a heat pump for heating or cooling. Other uses include combined heat and power, solar power generation, Stirling cryocoolers, heat pump, marine engines, and low-temperature difference engines. Alternatives. Alternative thermal energy harvesting devices include the Regenerator. Thermogenerators allow less efficient conversion but may be useful in situations where the end product needs to be electricity and where a small conversion device is a critical factor. See also. References. Bibliography. Further reading, RCB Lair. Device for decreasing the startup time for Stirling engines, U.S. Patent 4,057,962. Granted to Ford Motor Company, November 15, 1977. Ph. Separately. A pistonless Stirling engine The traveling wave heat engine. Journal of the Acoustical Society of America 66, 1508-1513. Bibcode, 1979 ASAJ. 66.1508 CDOI, 10.1121/1.383505 P. Fett. About the efficiency of the Regenerator and the Stirling engine and the function of the volume ratio VMAX/VMIN. Retrieved January 19, 2009. P. Fett. A twice double-acting I plus or minus type Stirling engine able to work with compound fluids using heat energy of low to medium temperatures. Retrieved January 19, 2009. D. Hayward. An Introduction to Stirling Cycle Machine. Retrieved December 20, 2013 11:13 p.m. WATR, Z. Herzog. Stirling Engines. Mont Alto, Pennsylvania State University. Retrieved January 19, 2009. F. Kai Manu. A. Abodiko. Solar Stirling Engine Water Pump Proposal Draft. Retrieved January 19, 2009. Lund University, Department of Energy Science, Division of Combustion Engines. Stirling Engine Research. Retrieved January 19, 2009. N.P. Nightingale. NASA Automotive Stirling Engine MOD2 Design Report. NASA. Retrieved January 19, 2009. D. Phillips. Why Aviation Needs the Stirling Engine. Retrieved January 19, 2009. External links, Stirling Engine at DMOZIURILI. Stirling Cycle Machine Analysis 2008 Winter Syllabus, Simple Performance Prediction Method for Stirling Engine, Explanation Stirling Engine and Demos, Shockwave 3D Models, Beta Stirling Unlimited.